Our modern world essentially runs on fiber optic communications technology. On our increasingly connected planet, nearly everything we do, from making a phone call to checking our bank account balance, to yelling at computers to tell them to turn the lights off, to watching this very video, almost certainly relied at some point on turning your voice or input or the data making this image into incredibly brief, incredibly fast pulses of light, firing that light with a laser down a glass pipe and counting the pulses on the other end. And probably doing that a whole bunch of times over potentially thousands of kilometers nearly instantaneously. And yet, in the consumer space, fiber optics are almost nowhere to be found. We send digital video data over these complicated cables with upwards of a dozen little strands of copper inside them. Networking equipment in homes and businesses still uses Ethernet, twisted pairs of copper wire that need to be made more precisely with higher tolerances each time we want to push the speed up another order of magnitude. Really, we just haven't seemed to find a place for fiber optics aside from piping the internet into your home or business, and even then, that's not exactly common. Except there was that one time Toshiba decided to connect CD players to amplifiers with fiber optics in 1983. Yes, although fiber optics may seem like the upper echelon of communications technology, and in fact, kinda are, there has been one consumer-grade fiber optic standard floating around since the early 80s. That would be TOSLINK, which is a shortening of Toshiba Link. In this video, we're going to learn a little bit about this surprisingly old optical standard. Ah, the compact disc. What a beautifully engineered medium for storing uncompressed digital sound. As you likely know, these things store data in millions of little pits and lands, and when you shine a focused laser on those bumpy bits, the varying depth causes destructive interference and results in a reflected beam that flashes light and dark, representing ones and zeros. Note that a pit doesn't mean 1 and a land means 0, rather the transition from pit to land or land to pit means 1, and a period of no change means 0. A CD player has to do a fair bit of processing before it can turn that raw data stream into sound. First, it has to translate the 8 to 14 modulation of the pits and lands to reveal 8-bit words. Then it has to parse the various signaling within that data stream for things like track and time markers. And finally, it has to work through the cross-interleaved Reed-Solomon coding to actually get the individual samples that make up digital sound. Once we're at that step, we can send those decoded samples to a DAC in order to be turned into electrical impulses that will drive headphones or loudspeakers to impart mechanical impulses into the air that we hear as sound. If you'd like to learn more about the compact disc and how digital sound works, you can check out these previous videos of mine. Now, without a DAC, we can't turn those samples into sound. Since that's the primary goal of a CD player, the CD player itself contains a DAC and generates a line-level analog audio signal to be sent to an amplifier over garden variety RCA cables. And for almost all intents and purposes, this is perfectly fine. Unless you cross the line into audiophile territory, you are probably delighted by the sound coming from these two little jacks. And so, for most of us, that's the end of the story. But the act of playing a CD is the very last step in the life cycle of producing a sound recording on compact disc. In the studio, digital tape machines are creating digital recordings from microphones or other analog sources, and various editing equipment needs to access those recordings to be manipulated and eventually mastered into a compact disc. All of this is different today, but just pretend like it's 1985, okay? Everyone's doing it anyway. Knowing that there'd need to be some standard way to move digital audio streams around, Sony and Philips, the co-creators of the compact disc standard, developed SPDIF, which is often pronounced SPDIF, because let's face it, that's more fun. SPDIF stands for Sony Philips Digital Interconnect Format, or you might also see Sony Philips Digital Interface. When Sony and Philips hammered out the details on SPDIF, they were using standard coaxial audio cables like these to send the digital data over garden variety copper wires. And that worked fine, no one was complaining. But then Toshiba got into the CD player business, and they wanted to be able to send the raw digital sound data recovered from the CD separately to an amplifier, letting the amplifier's built-in DAC do the digital to analog conversion, potentially reducing noise and interference. So they did. But someone at Toshiba was apparently dissatisfied with the ordinary nature of RCA cables. It's the future! We're using lasers to read sound from these miraculously small polycarbonate discs, and you expect us to convey the data they contain using wires? What kind of technologically regressive firm do you think this is? We are Toshiba. We make the future. And so they did. And really, what they did isn't all that remarkable. See, sending SPDIF signals over copper wire simply involved having a voltage repeatedly switch from high to low. SPDIF uses biphase Marc code, also known as differential Manchester encoding, to make the signal's clock part of the data stream itself. But now we're getting to specifics that don't really matter. Because of this fun little truth nugget, TOSLINK transmits the same exact SPDIF signals. Yep, TOSLINK is nothing more than a fancier way to send a SPDIF data stream to another device. Rather than using a wire and pulsing a voltage through it, TOSLINK uses optical fiber and a pulsing light. Of course, the sending device had to run a pulsing voltage through an LED to create that pulsing light, and then again the receiving end has to use a photodiode to turn that pulsing light to a pulsing voltage, so when we get right down to it, is there really a difference at all? Well, yes, but kinda no. And also, it's complicated. Firstly, I don't want to sound overly harsh here towards TOSLINK. Sending a signal through optical fiber is not only objectively cooler, but does have some advantages. Though even that's debatable. And secondly, while TOSLINK is indeed a fiber optic communication standard, it is in no way comparable to the fiber optic networking equipment that makes up the backbone of the internet. So while TOSLINK may not have much to brag about compared to a simple coaxial SPDIF connection, this isn't to say fiber optics aren't important. But back to TOSLINK. One of the stranger things about it is that its history seems almost entirely unknown. I've been looking for some sort of patent related to it but haven't had any luck, and even if Toshiba did patent it, it looks like they just let it out into the wild. It was fairly common on high-end CD players by the late 1980s, and in 1987 it was referred to as an ad hoc standard by Digital Audio and Compact Disc Review. So it looks like, though Toshiba may have created it, and they appear to have the trademark on the word TOSLINK, they let pretty much anyone who wanted to use it, use it. It just sorta happened. Indeed, the TOSLINK connector and cable specifications were adopted by the Electronic Industries Association of Japan as EIAJ RC5720. The physical bits of the TOSLINK standard are actually pretty darn simple. Take a look at an optical audio output and you'll see it glows with the red light of an LED. Some people think TOSLINK uses lasers, but it's just an LED. It's much cheaper and works fine. Taking a look inside the device reveals that, well, there's not a lot going on behind the scenes either. It's just a molded bit of plastic to hold onto the connector and align the tip of the cable with the LED. The cable itself isn't really special either. While some high-quality cables will use bundles of very thin glass strands, many are simple 1mm plastic fibers that run from one end to the other. Pretty much just a strand of fishing line. You can see that the cable will pass light through it no matter how it loops around, though if you introduce an extreme kink, you can damage the cable. With it plugged into the back of this CD player, you can see that now the other end glows, ready to pump that pulsing light into another device. On the back of an AV receiver or other sort of amplifier, you'll see some other TOSLINK connections, though these don't glow. Well, some of them might if it's also got a return out for something like a digital audio recorder or a minidisc player or whatever, but if it's the receiving end, it's as dark as the future of Windows Phone. Inside is a photodiode which will produce a voltage when it sees light, and thus will be able to reproduce the pattern of light pulses it receives as a pattern of voltage pulses to be processed, interpreted by a DAC, and finally turned into sound. It wasn't just CD players that used TOSLINK. Wait, I already mentioned minidisc. Pretend I didn't. Rewrites are hard. As more digital formats appeared on the scene, like digital audio tape in 1987, it was common to see TOSLINK inputs and outputs on mid to high-end equipment. Fun fact, the advent of consumer digital recording really freaked out the recording industry, as now it was possible to create bit-for-bit perfect copies of a CD onto a digital audio tape cartridge. While TOSLINK wasn't the only way to accomplish this, it was pretty widely supported by then, and we may have this little cable to at least partially thank for the Audio Home Recording Act of 1992, the later Digital Millennium Copyright Act, and the subsequent DRM schemes that would be cooked up in the decades to come. Thanks, Toshiba! One of the more interesting things I ran across was a seemingly needless design detail that hints at a never-realized upgrade to TOSLINK. See, the connector itself is keyed, meaning it can only be inserted with one orientation. This isn't necessary given that the optical fiber itself is centered, and there's only one of them. I honestly never even thought about this. If, however, there were two fibers in the same cable, say one for transmitting data and another for receiving, there would need to be a way to ensure the fibers in this two-way cable are correctly aligned with the connector. It's possible that the TOSLINK connector was keyed for just such a cable design, though this never came to fruition. Cool. So TOSLINK is a simple way to turn SPDIF into light, push it through a pipe, and then turn light back into SPDIF. But, why? Well, here's where things start to seem a little superfluous. One of the key advantages of using an optical fiber to send data is that it's not subject to electromagnetic interference. Normal audio cables like these can pick up humming or whining or any other sort of noise because they act like antennae. But if we're in the digital realm, what difference does that make? Sure, a coaxial cable carrying a SPDIF signal can pick up noise, but unless that noise gets so phenomenally bad that it somehow overpowers the very powerful and not at all ambiguous high-low pattern the cable carries, it doesn't matter. Analog noise in a digital signal doesn't come out in the processed result. This has always seemed more than a little weird to me. TOSLINK's signature advantage, that it's immune to electromagnetic interference, would only really be a selling point if it were transmitting analog signals. But it isn't. For the most part, either a digital signal gets through or it doesn't. Until the signal gets so bad that the receiver can't piece it together correctly, it will sound exactly the same. And once problems do show up, it's going to get glitchy or the signal will just drop out. It's not going to sound worse. It won't sound right at all. So choosing TOSLINK over coaxial because it is impervious to RF interference or other electrical noise is, well, I'd argue rather uninformed. Your amplifier circuitry doesn't care how it's getting that data, and once it gets to the DAC, we're well past the point where cables could make a difference. Now, it can be argued that having your audio devices entirely electrically isolated from one another could be advantageous because it prevents freak occurrences like a huge electrical spike through your RCA jack cooking a chip on your amp or something really unlikely like that. Though, if you're really worried about electrical isolation for sound quality purposes, good luck avoiding the building's electrical wiring they're eventually going to share. And then, well, TOSLINK actually has a lot of disadvantages. The most significant practical issue is that the longer the cable gets, the harder it is for light to reach the other end. Remember, this is largely a consumer standard, so even the most premium cables aren't anything near optically pure, and the longer they get, the more they reduce the amount of light that gets through. Add to that the fact that it's only got a weedy little LED lighting the whole thing up, and you get a maximum cable length of 5 meters. In practice, this can be and is regularly exceeded, especially with the brighter LEDs and with more sensitive photodiodes of more modern equipment. But with a coaxial cable, you can go a lot farther before issues crop up. Now, I don't want to get too far into comparing TOSLINK to a coaxial SPDIF connection, because that means getting into incredibly nitpicky details like clock jitter that you shouldn't even look up, because trust me, it will just make you question your sanity. So instead, let's talk about mini TOSLINK. Since the only part that actually interfaces with the LED and photodiode is this little nib, the mini TOSLINK connector was created to allow optical audio connections in the same form factor as a 3.5mm audio jack, and indeed to combine optical audio and analog audio into a single port. This, by the way, is perhaps the greatest proof that the keying in the standard TOSLINK connector was completely unnecessary unless they had future plans. The TOSLINK part of this is just an itty bit longer than a normal audio jack, just to make sure when you plug in headphones or whatever you don't poke the LED or photodiode. Fun fact, I didn't know this was a thing until I was messing about with my Chromecast audio, unplugged the audio cable from it, and the hole started glowing. I kid you not, I did not know mini TOSLINK was a thing, and I learned about it by accident. I don't know exactly how common it is in the grand scheme of things, but it allowed portable devices like this mini-disc Walkman to record from an optical source. Neat. Apparently it was found in some laptops and other random junk. I hope it wasn't like super common and I've just missed this until 2016 or whatever. By the way, if you go to Amazon and search TOSLINK cable, you'll find that some of the more popular options feature gold-plated connectors. So far, optical audio connections have really withstood the test of time. It's pretty impressive that a digital standard introduced in 1983 is still quite common in consumer audiovisual equipment. Loads of new TVs feature an optical audio out, as do game consoles, Blu-ray players, and even some streaming boxes. Recently, that started changing for reasons we'll get into, but on the whole, it's still a pretty common sight in 2019. A large part of why it's still so common is that in addition to uncompressed stereo PCM audio, TOSLINK also supported compressed 5.1 or 7.1 surround sound using Dolby Digital or DTS. Since loads of AV receivers going back to the 90s will still be able to process at least some of the data streams coming from a Blu-ray player or smart TV, it's been remarkably future-proof. Also of note is that the physical specifications of TOSLINK were borrowed in the ADAT light pipe or ADAT optical interface. This professional standard carries up to 8 channels of uncompressed PCM audio using the same hardware as garden variety TOSLINK connectors and cables, though this high bandwidth signal is entirely incompatible with our old friend Scheibe. So then why is TOSLINK apparently on its way out? Well, because of the same thing I said was an advantage a few moments ago. It's not been updated, like at all. One of the things Blu-ray brought us was uncompressed surround sound formats like Dolby True HD, and TOSLINK doesn't have the bandwidth to support that.
You just said ADAT light pipe could carry 8 channels of PCM audio.
You're right, I did, but that's not actually TOSLINK or Scheibe. It just uses the same cable and connectors. See, it would be relatively easy to just make the LED go blinky blinky a little faster and thus increase the bit rate of the data coming through the cable. But that means creating a new standard to be agreed upon by all the manufacturers out there. And that can be difficult. See, I can connect this brand new television to this AV receiver from the 90s over TOSLINK precisely because the standard hasn't really ever changed. If TOSLINK were updated, at the very least I'd need to tell the TV to downgrade its output to match this receiver's expected input, and that can get messy fast. Remember, this is one-way communication. Easier to just never change it up, you know? And then there's this other thing called HDMI. Yeah, the handy-dandy movie input not only transmits digital video at a bitrate that will put your CD player to shame, but it also transmits digital audio at bitrates that will put your CD player to shame. Poor CD player, you're doing all right. Since the very first HDMI version 1.0 debuting in December 2002, uncompressed 8-channel, 192 kHz, 24-bit PCM audio was supported. That's like way more bits. With all that bandwidth, high-resolution sound is no problem at all. Scheibe and thus TOSLINK sort of became obsolete once Blu-ray and even HD DVD appeared on the scene, offering lossless surround sound. HDMI could carry those signals no problem. Oh, and HDMI 2.0 introduced 32-channel audio, so we're fine now. Also, in 2009, HDMI 1.4 introduced the audio return channel. That's why one of the HDMI inputs on your TV is labeled ARC. This sends audio back through the HDMI cable to enable your soundbar or home theater system to receive the audio that your TV itself is producing, such as when streaming video on a smart TV or simply receiving over-the-air broadcast television. Yeah, HDMI has superseded TOSLINK on all fronts in the home theater space. As more soundbars and AV receivers support the audio return channel, TOSLINK increasingly finds itself in the legacy category, which is still just kind of weird. Fiber optics are capable of some insane bandwidths, and while TOSLINK hails from the age of 10 megabyte hard drives, you'd think that we'd have seen more fiber optic standards in the home. In the next video, we'll explore why fiber optics have remained little more than a novelty in the consumer space, and discuss whether any of our current everyday technologies could perhaps be better served with fiber optics. Thanks for watching. I hope you found this video to be as enlightening as it is digital. That is terrible. And yet, I still said it. Worse, I wrote it. I even wrote these words. How silly. But not as silly as selling TOSLINK cables with gold-plated connectors and claiming that makes a superior connection. Anyway, I still think TOSLINK is pretty neat and even futuristic, even though it's pushing 40 years old now. As always, thank you to everyone who supports this channel through Patreon, particularly the fine folks you see scrolling up your screen. Contributions from viewers like you make this channel sustainable, and I owe you my thanks and appreciation. If you'd like to join these awesome people in supporting the channel with a pledge of your own, you can find a link to my Patreon page in the description. Thanks for your consideration, and I'll see you next time. communication technology. On our increasingly connected planet, nearly everything we do, from making a phone call... I didn't get very far. Since the only way that... Whoop, uncompressed digital surround formats. That line is wrong! Oh no! That take might have been fine, but there were some weird bits. Also of note is that the physical specifications of pairs of copper wire that need to be made more precisely and with higher tolerances. We are on the second line, and recording is...